All right, open up your book to section 9-6. We're on page 463 in your book, and the title of this section is called Vector Addition. So the objective is given two vectors, add them to find the resultant vector. So this section here, we're going to look at another way to explore some of the problems that we've been working on in this chapter using vectors. All right, the first thing we need to do is talk a little bit about some vector terminology here. And so let's start out with just a vector in general. First of all, when you look at a vector has a head and a tail. And the way that we distinguish between those two is by indicating that the head has the arrow at the end of it. And that's actually indicating a direction for that vector. So the vector starts at the tail and it ends at the head there. That's the head and the tail of your vector. And the naming convention that our book is going to use for vectors is we're going to use just a single letter, and it will be lowercase. We'll usually start out with V, but if we have more vectors, then we'll go on from there and use other vector names. And we'll draw a little arrow over top of that vector name to indicate that it's a vector. So V with an arrow above it means it's a vector. All right, when you work with vectors, you have two components to that vector, two parts to that vector. A vector actually contains both a magnitude and a direction. So the magnitude of your vector is defined as the size or the length of your vector. And the way we denote that is we use the absolute value to denote that. The absolute value of your vector is defined as the magnitude or the size of the length. So again, without the absolute values, we're talking about the vector itself. With the absolute value, we're talking about how long that vector is, what's its magnitude. We also have a direction for a vector, and a direction is the angle that that vector makes. For the most part, we're going to work with vectors in standard position. However, we will talk a little bit about navigation bearings as another way to measure an angle. But you have to know which one of those you're using when you go to find the angle of your vector or to draw your vector. But the direction indicates the angle that that vector has. So that's the direction you are headed with that vector. All right, we have two different types of quantities that we talk about when we're working with vectors. We have what's called a vector quantity and a scalar quantity. And the book will refer to each of these here, and so it's critical that we understand which is which. When we talk about a vector quantity, it's a quantity that has both a magnitude and a direction. So a vector contains a vector quantity because it has both a magnitude and a direction. On the other hand, a scalar quantity is a quantity that has just a magnitude, no direction. So in other words, it's a single value. It'll be critical for us to recognize when we're working with vector quantities, because there's two parts to that, versus a scalar quantity, which means it has just a single part to that. All right, and the last term here that we want to talk about is what it means to be equal vectors. When we have two vectors that are equal, that means that you have vectors with the same magnitude and direction. Notice that this does not say that they have the same head and the same tail. It just has to have the same magnitude and direction. What that means is it allows you to take a vector and translate it. I can move it, shift it horizontally or vertically, and I end up with the same vector. I end up with an equal vector. All right? Those are equal vectors, same magnitude and same direction. All right, so let's take a look at an example here. Look at example number 1 here on page 464. They give us this picture here to go along with it, actually on the previous page, but it says you start at the corner of your room. So that's where you see in the bottom left of that picture. You start at the bottom left there in the corner of your room, and you walk as shown there in figure 9.6a. Okay, so let me just draw on top of this here. So you're starting right here. This is our starting point. You're starting in the corner. And then you're going to walk 10 feet in this direction. And it's 10 feet at an angle of 70 degrees to this wall here is what we're looking at. And then we change direction. We then turn 80 degrees to our right, and we walk for 7 feet in that direction. And we end up at this point right here. We end right there. Okay, so that's the path that we're taking there. The question here is to find the displacement that results from the two motions. So what we're looking for is, if I draw, and they have it as a dotted vector, I'm going to just make this a solid red vector there. That vector right there, I'm going to call that vector V. That vector there represents the resultant vector of this path that I took. I traveled in one direction for a while, then another direction for a while, and if I compare where I started to where I ended, that is the resultant vector that goes from the start to the end. All right, so the question is, what's the magnitude of that vector? Is another way of asking what they've stated here. It says find the displacement. That's going to be the same as the magnitude of this vector. Well, the good news for us is we've done quite a bit of work here with triangles, and that's what we're looking at here in this problem. We basically had ourselves an oblique triangle, and I am being asked what's one of the side lengths. I know two of the side lengths. What's the third side length is really what they're asking for. All right, so to answer that question, we've got to do a little bit of work here with this sketch to be able to come up with some key angles here for us. But once I know that, I can come up with what the displacement is here. So opposite this vector, I'll do it in the same color, is this angle right here that would be in our triangle. And if I look at the green vector here that I've got sketched, if I look at that vector, I've got part of this is 80 degrees, and then this other chunk here that I just marked is the part that's in my triangle. The sum of those two has to be 180 degrees. This is a straight line there. So with that, I can find out that this must be 100 degrees. Okay, I can find out that angle there. Look carefully at your sketch, figure out how exactly your angles are related. Look for parallel lines, look for transversals. There's a number of things we can do to help us come up with what these angle measurements might be. This one is pretty straightforward because we have a straight angle, and so I can figure out that the angle in my triangle is 100 degrees. So with that, we can use law of cosines now to find out what the, we can use law of cosines to find out what the displacement is, or really the magnitude of that vector. So I'm going to write it as the magnitude of my vector v squared, right? Law of cosine says you take that side squared and you set it equal to, it'll be the 7 squared plus the 10 squared minus the 2 times 7 times 10 times the cosine of my angle, which we just came up with was 100 degrees, the angle that's opposite the side that I'm looking at here on the left side. So there we go. We just got to plug that into our calculator and find out what the magnitude of vector v is. So grab your calculator and let's try that out. All right, so for vector v, if we just take 10 squared and add on the 7 squared and subtract the 2 times 10 times 7, I think I actually wrote that in the other order, but same calculation, of course, times the cosine of 100. And make sure you're in degree mode there, and we should end up with the magnitude of our vector squared. So let's take the square root of this. Now there we go, 13.165, I guess, if we round that. Let me grab a picture of that. All right, and let's write down what, I guess we can write down both of these, what v squared is equal to, or the magnitude of v squared is, magnitude of our vector squared, I should say, is the 173.311. But again, we're looking for what the magnitude of that vector was equal to, so take the square root of both sides like we did, and we got 13.165. 13.165 if we round that. And include units here. Again, the distances they gave us here in this problem were in feet, so that would mean that this is 13 feet. So we're 13 feet from the corner of our room is what that tells us. 13 feet from where we started. Now that's really all they asked us to do in this problem, but let's go a little bit further here, because many times they're going to want to know not only the magnitude of the vector, but also its direction. So let's tackle that part of it as well. So what is the direction going to give us? All right, so let's go back up here and let's name a couple of things here. We know this one angle that they gave us here. We've got that marked in green. That was the 70 degrees. That's this angle right here. That's 70 degrees. The direction, though, that I need is this vector to this red vector that we've got here. Is this angle right here. That's the angle that we're looking for. So I'm going to call that theta. That's the direction of my vector. But notice theta is not in my triangle. Theta is outside of my triangle. But I can use that to help me come up with the angle that's in my triangle. I guess I did that in purple. I'll draw this in purple here. This angle right here is opposite that purple vector that I got up there. That angle right there is actually the difference between these two angles. If I take the 70 degrees, the full angle, and subtract off this theta, that will give me this guy right here. This is 70 minus theta is that angle. 70 minus theta. So I can use law of cosines again to find out what 70 minus theta would be equal to, and then I can solve that for theta to find out the direction of my vector. All right? So let's do that. Law of cosine. So again, the angle that we're looking for is the 70 minus theta, so I have to use the 7 as the opposite side here. So it's going to be 7 squared is equal to, so it's the 10 squared. I'm going to go ahead and just write this as the magnitude of vector v squared. If you want to write down the 13.165 and square it and write it that way, that's fine. But we'll just substitute that quantity in here when we go to solve this. So subtract off 2 times 10 times the magnitude of vector v times the cosine of this 70 degrees minus theta. Again, our goal is to find out what theta is equal to. I want the direction of my vector. All right, well, we've done this many times now with law of cosines. You got to subtract off the 10 squared and the magnitude of vector v squared. So 7 squared minus 10 squared minus the magnitude of vector v squared is equal to the rest of this. 2 times 10 times the magnitude of vector v times the cosine of, oops, I lost that, cosine of 70 minus theta. And now divide by that negative 2 times 10. So 7 squared minus 10 squared minus the magnitude of vector v squared all over negative 2 times 10 times the magnitude of vector v. And that's equal to the cosine of 70 minus theta. Now again, to solve this, we're going to use arc cosine technically, but remember, we're looking for an angle that's in a triangle, so actually I just need the cosine inverse solution to this. So let's go ahead and punch that quantity we have over there on the left into the calculator and get a decimal approximation for that first. That'll make it a little bit easier to write this. Let's go ahead and grab your calculator. And I guess I can get rid of, actually before I get rid of that, let me store that value. I'm just going to store this into v here. It was the magnitude of v here, but let me store that value because I'm going to need it. All right. And so we're going to calculate, move this over here. I want to calculate that 7 squared minus 10 squared minus the magnitude of v squared. That's what I'm trying to calculate. So I've got 7 squared minus the 10 squared minus the v squared. I stored that too. And we have to divide that by a negative 2 times the 10 times v. All right, so we get 0.851 or 852. So we can write it that way. 0.852. So I've got 0.852 is equal to the cosine of 70 degrees minus theta. All right, again, solving for theta. Let me rewrite this with the cosine over here on the left side, actually. Cosine of 70 degrees minus theta equals your 0.852. I guess I could have rewritten it that way up above. And now technically we're going to use arc cosine to solve this, but again, I already know that I'm going to use the positive part of that, and I'm going to let n be 0. So we can simplify this. If I'm solving for an angle, that's going to be in a in a triangle, not a right triangle, but an angle in a triangle there for us. And I'm solving for theta, so what does that mean theta is equal to? It's going to be the 70 minus this cosine inverse, right? All right, so if we grab our calculator, we can punch that in and see what we end up with. 70 minus the cosine inverse of that value we just calculated. So if I take 70 minus the cosine inverse of that answer that we got, and we get 38.423, I guess. Let's go ahead and grab a screenshot of that. All right. So we have theta is equal to 38.423. That's going to be in degrees. That is the direction of our resultant vector. Again, they didn't really ask us to come up with that in this problem, but that gives us both the magnitude and direction of our vector. All right, so let's talk about what vector addition is. That's the title of this section. And so here's what vector addition is defined as. If you take two vectors, A and B, like you see over here on the right, I've got vector A and vector B, and you place them so that vector A and B are head to tail. The head of vector A and the tail of vector B are at the same spot. And you can do it either way, actually. You could write the tail, you could put the tail of vector A at the head of vector B. It would be the same resultant vector here. But the sum, A plus B, is the vector from the tail of A to the head of B. Technically, if you write the vectors the other way around, then technically it would be B plus A, but vector addition is commutative. In which the, from the tail of A to the head of B, in which the tail of B is placed at the head of vector A. So that's what you see there, that the key to this is you have to place these two vectors here so that the head of one vector and the tail of the other vector share the same point. And then the sum of those two is just the vector that starts at the tail of vector A and ends at the head of vector B, as you see. That's vector addition. And so what exactly is the resultant vector? Well, the resultant vector is defined as the vector resulting from the sum of those two vectors that we've got there. So the resultant vector is the vector that we have in blue. And when you take two vectors, add them up, the resultant vector is the vector that goes from the tail of the first one to the head of the second one. All right, so let's take a look at example 2. Example 2, they give us a ship near the coast is going 9 knots at an angle of 130 degrees to a current of 4 knots. And they define a knot for us. A knot, or KT, is a nautical mile per hour. So it's a rate, slightly faster than a regular mile per hour. What is the ship's resultant velocity with respect to the shore? All right, so to start off with this problem, let's draw ourselves a sketch here of these two vectors. They don't tell us the direction of the individual vectors. They just tell us the angle between the two of them. So that's what we want to sketch here. So they told us the ship is near the coast. It's going 9 knots at an angle of 130 knots to a current of 4 knots. Okay, so let's sketch our vectors here. I'm going to draw one of these vectors as being horizontal. Since they didn't tell me which one here, I can, or a direction for either vector, I can pick the direction I want. The key is that the angle between them, which I'll draw the other one like this, that angle between them has to be 130 degrees. That's what they told me. All right, so let's draw this with the 4 knot vector, which is the current, will be horizontal. I'm going to make this vector here 9 knots. All right, and the question is, what is the ship's resultant velocity with respect to the shore? Now notice that the way I've got this sketched, that I've got the two tails here, of the two vectors lining up. I've got these two vectors tail to tail. If I'm looking for the resultant vector is the vector that goes from the um, tail of one vector to the head of the other one, as long as the two vectors are lined up head to tail, which obviously we don't have that situation yet. So we've got to translate one of these two vectors. And it really doesn't matter which one of the two you pick to translate. I'm going to take the vector that's horizontal, I'm going to translate him, and I'm going to rewrite him, or redraw him, so that he is up here. This right here is going to be my 4 knots. So I'm just simply taking that vector down here, and I've translated up. And now, by doing so, I now have two vectors that are lined up head to tail. And so now the vector that goes from the tail of the first vector to the head of the second vector, that right there is our resultant vector. All right, and I'm going to go ahead and call that vector v. Sometimes I might call that r for resultant, but I'm going to call it vector v again. And the question that they're asking us is, again, what is the ship's resultant velocity? They're asking me for the magnitude of that vector. All right, so got to be able to read through the problem first of all and figure out what exactly are they describing. Draw yourself a picture of that. Once you have yourself a sketch, now let's solve the question they're asking for. So they want us to find the magnitude. This sounds a lot like the previous example that we just did. I'm going to use law of cosines to find the magnitude of this vector. Now before I do that though, I need to find an angle. And so to find that angle, we'll use a little bit of geometry to help us out here. I'm just going to draw this as a dotted line here. Realize that this line right here, that vector right there, and since I translated it, this vector up here is parallel to that vector that I have down below. Those two green lines or dashed lines are parallel to each other. This right here, vector, which is my speed of my boat here, which was 9 knots, or a ship, whatever it is a transversal cutting through those two parallel lines. So what I know about that is that a transversal that cuts through parallel lines has alternate interior angles that are equal to each other. So if this angle right here is 130 degrees, then that means this angle right here must be 130 degrees as well. And if that's 130 degrees, again because of the straight angle that I see there, I can measure this angle right here that's opposite my vector v that I'm looking for, and that must be 50 degrees. The sum of these two has to be 180 degrees, so 180 minus 130 gives me 50 degrees. Again, we can find the measure of that angle. Just carefully analyze the sketch that you've got there. Think about using your properties from geometry in this case, or whatever it might be, to help us come up with our angles. All right, once we got an angle, we are all set here. Use law of cosines. So the magnitude of vector v squared is equal to 4 squared plus the 9 squared minus 2 times 4 times 9 times the cosine of the 50 degrees that we just came up with. All right, this looks like another calculator problem here, so let's grab our calculator and run that calculation. All right, so we have 4 squared plus the 9 squared. And we're subtracting off the 2 times 4 times 9 times the cosine of the angle that we just found in between them, which was the 50 degrees. Now again, this finds the magnitude of that vector squared, so let's take the square root of that. And we end up with 7.122, I guess, if we round that. Let me grab a screenshot of that. All right, so I'll go ahead and write down both calculations. You can just simply write down what the magnitude of your vector is. Would be certainly fine to do here. But the magnitude of my vector v squared was 50.719. And then when we took the square root of that, we ended up with the magnitude of vector v, which was 7.122. And that was in knots. Okay. Now again, the question that they asked you here was, what is the ship's resultant velocity with respect to the shore? That actually answers the question. That tells us our resultant velocity. But again, it might not be uncommon for them to also ask you for the direction of that vector. So if I want to find the direction of that vector, I can go about this the same way. The direction of my vector that I'm looking for is this angle right here. That's my angle theta. And I know the whole angle here in green is 130 degrees. So to get an angle that's in my triangle, let me do that in blue, this angle right here would be 130 minus theta. It's 130 minus theta. That's an angle in my triangle. So now I can use the law of cosines with that guy right there to come up with my direction. So let's go through that and find that direction. All right, so the side opposite that angle was the 4. So I've got 4 squared is equal to the 9 squared, and I'm going to write this as just the magnitude of v squared, and then minus 2 times 9 times the magnitude of v, and then times the cosine of, what was that again, 130 minus, yeah, 130 minus theta. And again, we're trying to find out what theta is equal to. That's the direction of our vector that we're looking for. And so solve this like we've solved this many times before. I'll again do it in a couple of steps here, but you could kind of combine some steps. That would be certainly fine to do if you're comfortable doing that. So first subtract the 9 squared and the v squared. The right side stays the same here then, or what's left I should say stays the same. Oops. And now divide by this coefficient, the negative 2 times 9 times the magnitude of vector v. That's the cosine of 130 degrees minus theta. And again, we can grab our calculator here and approximate or find what this is equal to approximately on the left side here. Let's do that. Let me store this value into v here, since that's what I called that vector, v. And I can get rid of that. So we have, gotta remember my calculation here again, it's 4 squared minus 9 squared. Okay. So we got 4 squared minus our 9 squared minus the v squared. And we're dividing that by a negative 2 times 9 times v. All right, so 0.903, I guess, is what we'll write that as, 0.903. I'm going to write this as the cosine, over here on the left side, cosine of 130 minus theta equals the 0.903. And again, to solve this for theta, we've got 130 minus theta is equal to the cosine inverse of the 0.903. Again, I don't have to use arc cosine because I'm looking for an angle in a triangle. So I know I'm going to pick the positive cosine inverse. I'm going to let n be 0. And now to solve for theta, theta is going to be 130 minus that cosine inverse of the 0.903. Let's grab our calculator and evaluate that. So if I take 130 minus the cosine inverse of that previous answer there, actually, 104.516. 104.516 is the number we're looking for. That is the direction of our vector here. .516. All right. And that was a little bit more work than what they asked us for in this problem, but that at least shows us how we can come up with our direction again if we're looking for that. All right. Let's talk about a couple of different ways that you can measure angles. You now are very familiar with the first way. At least I hope we're very familiar with the first way, which is measuring angles from standard position. And when we talk about measuring an angle from standard position, we're talking about 0 degrees is the positive x-axis. You measure this in a counterclockwise direction to get a positive angle. So 90 is the positive y-axis, 180 is the negative x-axis, 270 is the negative y-axis, and back around to 360 or 0 there back at the positive x-axis there. That's standard position, measuring angles that way. All right, we're very familiar with that. Basically everything we've done with working with angles since we started trig has been working in standard position. However, in this section, we're going to see some other ways to work with angles, and in particular, we're going to work with angles that are navigation bearings. So this is what a navigation bearing is. When you're looking at a navigation bearing, first of all, your navigation bearing theta there is going to be between 0 and 360. It can be equal to 0, but it can't be equal to 360. So it does not get bigger than 360, it does not get less than 0. And so what you have here is your north, south, east, west. North is 0 degrees, and we measure this in a clockwise direction now. So as you go around clockwise here, east would be 90 degrees, or that would be the positive x-axis. South is 180 degrees, or that would be the negative y-axis. West is 270, which would be the negative x-axis, and then back around to 0. Again, we don't hit 360 there because we can't be equal to 360. We reset back to 0 at north. That's the positive y-axis. So when they give you a problem there that's working with navigation bearings, just realize this is how they're talking about measuring angles. So when you go to sketch things and they tell you that you've got a bearing of 100 degrees, just make sure you sketch it accordingly to this way here. All right? You'll measure this from a navigation bearing, measuring from the positive y-axis and going clockwise to find that angle they're giving you. All right, although we'll talk a little bit more about that in the second half, but I just want to make sure you understand what a navigation bearing is and how we actually measure those, and that will allow you to answer some questions about navigation bearings. All right, that right there is the end of the first part of section 9-6.